Hello and welcome back to Algebra 2. Today we are looking at the properties of logarithms. So in the previous sections we learned how to solve for x in the exponent using logarithm. So now I want to know what are some of the other things that you can possibly do with log. So here what I have written out are the following. I wrote out the log of 2, log of 3, log of 4, log of 5, all the way to log of 10. Just, if you were to take your calculator and plug them in and, get these as a result. From here, it doesn't look like it's much because, you just see basically a whole bunch of numbers. And some of this you should actually recognize because, log of 10, you should actually know that that's equal to 1. Since it's saying 10 to what power is equal to 1. So that is the one that you want to memorize, if anything. But if I take a look at these properties, if I take a look at these numerical values of the logarithm, you'll notice that there are actually some properties that we can get out of it. Or I'm sorry, it's more like some of these numbers, they kind of, have some things in common. So for example, let's take a look at the log of 2, right? And then if I take that and add it with the log of 3, let's see, that is equal to 0.301 and then plus 0.477. And if I add those together, that is going to be equal to 0.778, which looks like it's the same thing as the log of 6. So, that's pretty interesting. Let's take another one right here. If I take the log of 2 plus the log of 4 in this case, so that's 0.301 once again, plus the log of 4, which is going to be 0.602, that looks like it's equal to 0.903, which looks like it's equal to the log of 8. So here, let me go ahead and write that down then. So this is equal to log of 8, and this is equal to the log of 6. Let's take one more. How about, let's say we have the log of 5, and then add that with the log of 2. So the log of 5, that is going to be 0.699. And then add that with the log of 2, because, we've been using it so often, is 0.301. And if you add that together, that is equal to 1, which is equal to the log of 10. Now, taking these things, you'll notice that here, log of 2 plus log of 3 is equal to log of 6. Log of 2 plus the log of 4 is equal to log of 8. Log of 5 times the plus the log of 2 is equal to log of 10. We can probably get a pretty good idea as to what's happening here. So it looks like, in conclusion, the log of some number plus the log of another number is equal to the log of those two numbers multiplied together. So that right there is a pretty interesting idea right there, right? And hopefully, that can kind of somewhat make sense to you because remember, logarithm is really just an exponent, right? Logarithm is really just an exponent. So it only makes sense that if you add those two exponents, you're going to be multiplying them in some way. Now, we technically haven't proved this yet, so we're going to have to do this right now just so that we can kind of verify them, okay? All right, here is going to be, well, our derivation in this case then. So like we said, the log of a plus the log of b is equal to the log of a times b. Now, before I prove this, I need to do a small little proof on the side, what we call lemma, if you remember how this works. A lemma is basically a small little proof that we use to prove a bigger proof. So in this case, our lemma is 10 to the log of a is equal to a. 10 to the log of a is equal to a. Now, this one right here, if I use the definition of logarithm, basically take the log of both sides, you will get the log of a is equal to the log of a, because here I took take the log of both sides. Okay, and you can see how log of a is equal to log of a. All right, now that that's out of the way, I want to go ahead and use this lemma to actually help me out here a little bit. Okay, so here is what I'm going to do then. I'm going to go ahead and say a times b is equal to a times b. So that's pretty straightforward for the most property. That's just the reflexive property, right? Now, according to the lemma that I just gave you, then 10 to the log of a multiplied by 10 to the log of b is equal to a times b, because I'm replacing a with the 10 to the log of and then b with 10 to the log of. So just using that lemma. On the left, you'll notice that I have an exponential setup where we have two exponents multiplied by each other. I'm sorry, we have two terms that have the same base multiplied by each other. So what that means is I can add the exponents together because that's the property of exponents. So 10 raised to the power of log of a plus the log of b is then equal to a times b. And now, just like with the lemma, the way we proved it, I'm going to go ahead and take the log of both sides. So if I do, then the exponent, which is log of a plus the log of b, is equal to the log of a times b. And right there you go. That's going to be our proof then. Okay. And we can actually make this a little bit stronger by doing the following. If I take our theorem over here, which we just proved, I'm going to go ahead and divide everything by the log of c, divide by the log of c, and then this guy over here, let me erase that a little bit, and divide by the log of c, then that gives us something that's a little bit stronger. That gives us the log of base ca plus the log of base cb is equal to the log of base c a times b. So we're no longer now restricted to base 10. We can just use any kind of base that we actually want then. Okay. So there it is. That's the big one right there. Now, there are other properties of logarithms because remember, if you think about what we just said earlier, logarithm, again, is an exponent. Here, we're saying that if you add the two logarithm, that becomes a product of the log. So then that means that there is going to most likely be a subtraction. So if I have the log of a minus the log of b, I want to prove that that's the same thing as the log of a divided by b. Okay, I want to prove that log of a minus the log of b is equal to log of a times a divided by b. Okay, for this one, so the question is, well, how do you prove it? Well, same as the last time. So why don't we do the following? Sorry about that. Why don't we go ahead and say that a divided by b is equal to a divided by b. So if we set that up, then according to my lemma, then we can say that 10 to the log of a divided by 10 to the log of b is equal to a divided by b. Now, the left-hand side again, we're going to go ahead and change that so that it's the base of, so that we can use the exponential property. 10 raised to the power of log of a minus the log of b. Because if you remember, if you have x to the a divided by x to the b, that's the same thing as x to the a minus b. Now, cutting the middleman over here, we can go ahead and take the log of both sides. So the log of a minus the log of b is equal to the log of a divided by b. And just like in the previous example, we're going to go ahead and make this proof a little bit stronger and have a base c on all of them. So we're no longer restricted to just base 10. And finally, for the last one, if I have the b times the log of a, that's supposed to be equal to the log of a to the b power. And if you're wondering, if you want to see example of this, let's go back to this previous part right here, in this little chart right here. I'm going to go ahead and erase some of this stuff right here. So let's see if we can kind of get rid of it, trash it over here, and then trash it. Oh, well, it's kind of strange here. Let's see. Oh, there we go. Now it's working out. Okay, here, consider the following now. Let's look at the log of 8 over here, which is equal to, according to our chart, 0.903, right? Another way of saying 8 is supposed to be 2 cubed, right? So if I take the log of 2, let's just have that as a starting point, you'll notice that that is equal to 0.301 according to our chart. Now, if I take this log of 2, which is equal to 0.301, what I can do is multiply 3 to both sides. And if I do so, then you'll see that this 0.301 becomes 0.903. And this right here would then be equal to the log of 8. So that is basically kind of our conclusion then. So 3 times the log of 2 is equal to the log of 2 to the third, which is the same thing as the log of 8. Take another one just in case then. Let's say this time, I don't know, what's a good one we can pick? Here we go. Let's say the log of 3, which is approximately equal to 0.477, right? If I go ahead and multiply that by 2 to both sides, then that 0.477 becomes 0.954. And if you look at 0.954, that right there is the same thing as the log of 9. So in conclusion, 2 times the log of 3 is equal to the log of 9. So in terms of, our exponential, properties, It's basically saying that, hey, if you have an exponent over here in the logarithm, you can go ahead and take it outside as a multiplier. So that's how it works for the last property. But anyhow, let's go ahead and do the quick proof for this one so you can see how some of these examples work. Here on the right-hand side, here's what I'm going to do. I'm going to go ahead and take this and rewrite it. So log of log of a to the b power. Let me go ahead and write that as the log of a times a times a times a times dot 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 times a b number of times. So b times. So if I can write it like this, then the next thing I can use is the first property, or sorry, the first proof that I have for logarithm. Take all of those log of a and write them out as an addition. So this right here is going to be equal to the log of a plus the log of a plus the log of a plus so on and so on so on plus the log of a. And there are going to be b number of those then, because we have b numbers of a inside. Well, if I have b numbers of log of a, then that's the same thing as saying b times the log of a, and right there, and that's going to be your proof. And once again, just like with all the other ones, I'm going to go ahead and put a subscript of c, so then that way we can go ahead and use it for not just base 10 then, okay? All right, now let's go ahead and look at some of the examples that you can use, that you can utilize these logarithm properties for. So the first part is that I'm giving you log of 2, which is equal to 0.301, log of 3, which is 0.477, and log of 7, which is equal to 0.845. What I want to do is I want to estimate the following over here using what's given to me, so then that way I don't have to use a calculator. So here in the first one, let's go ahead and solve for the log of 200. Now, to me, the log of 200, we're going to have to change that 200, kind of like prime factorize it. So I'm seeing it as the log of 2 multiplied by 100 inside the logarithm. As soon as I write that, then using the property of logarithm, I can say that that's equal to the log of 2 plus the log of 100, because we just proved that earlier. Log of 2 I have, that's equal to 0.301. Log of 100, now this one you should know because that's saying 10 to what power is equal to 100. So the answer for that one is just equal to 2. So now we're going to go ahead and add those two up. So the answer is approximately 2.301 then. So go to your calculator, check just to make sure. So the log of 200, so it's equal to 2.301, just as we said, okay? Now the next one over here, the log of 126, do the same idea. Take that 126 and try to prime factorize it as much as possible. So let's see, 126, I know it can be divided by 2. So the next one is going to be equal to 63 over here. 63, that goes into 9, and then that's 7. So that right there should work out. So this is going to be the log of 2 times 9 times 7. The log of 2 I can pull out as addition, plus the log of 9 I can pull out also, and then plus the log of 7 I can pull out. Log of 2 I have, that's 0.301. Log of 9, that's the same thing as the log of 3 squared, and then plus the log of 7, which is 0.845. Now, log of 3 squared, that 2, we can go ahead and pull outside as a multiplier instead of an exponent. So 0.301 plus 2 times the log of 3 plus 0.845. Let's see, so let me go ahead and add the 2 over there together. That looks like it's going to be 6 and then 4, and then that is a 1, so 1.146, and then plus 2 times the log of 3, which is 0.477. So doing a little bit of, grunt work math, no way to avoid this. 0.954. So taking all those, add them all up. So let's see, that's going to be a 0. That's going to be a 0. That is going to be a 1. And then that is going to be a 3, it looks like in this case. So am I doing it correctly? Nope, that's equal to a 2 in this case. Okay, so about 2.1 in this case. That's going to be my answer then. Okay. All right, so now let's try to kind of work backwards in this case. What I want to do now is I want to simplify the following without having to use a calculator. So rather than expanding the logarithm like I did in the previous problems, because notice that I did log of 2 plus log of 9 plus log of 7, what I want to do is I want to compress this so that there's one single logarithm, because maybe then there's going to be something simple that I can see what the answer is. All right, so let's see where we can go from here. Notice that they both have log base 8, so that's good because we can combine it. If they're not the same base, then you're going to have to do a little bit of work, and there's going to be, then we can't combine it just as easily. So here, let's go ahead and take this 1/2 and put it somewhere else because I'd like to combine the two logarithm together, and I can't do that with the 1/2 on the outside. So on the properties of, in the theorems of the logarithm, we can go ahead and take that 1/2 and bring it inside as an exponent. So 9 to the 1/2 power inside the log base 8 minus the log of base 8, 6. So now we're going to go ahead and clean that up. Log of base 8 and then 9 to the 1/2. That's the same thing as 3 because 9 to the 1/2 is equal to the square root of 9, which is equal to 3. Minus the log base 8 of 6. Now we can go ahead and combine these two together. Subtraction of two logarithm is going to be the same thing as the log of base of those two numbers inside divided by one from the other. So meaning 3 divided by 6 in this case. So 3 divided by 6, that is going to be equal to 1/2. So we end up with log base 8 of 1/2 right there. And that right there is as far as we can go in terms of using those using those theorems of logarithm that we just had. And this, even though it looks like it's the end, we can actually solve for this because if you remember from the last section, we said that log base 8 of 1/2, let's go ahead and call it x then. Then this is like saying 1/2 is equal to 8 to the x power. And that we can definitely solve for. So 2 to the negative 1 is equal to 2 to the 3x right there, getting a common base. So it looks like x is equal to negative 1/3. So that's going to be our final answer then. Okay. All right, thank you so much for watching, and I will see you guys next time then. Have a good one. Bye-bye.